So, good afternoon, dear students. Here we will do the application of Lindberg-Feller theorem. So, the first example is that xn is a sequence of independent random variables. Xn follows normal with mean 0 and a variance 1 by 2 to the power n minus 1 and goes from 1 to so on. So, you expectation xn is 0, so that expectation of Sn is also 0, and the variance of Sn is summation variance of xk, and this is summation k goes from 1 to n 1 by 2 to the power k minus 1. So you substitute the value of k is equal to 1 to up to n, so that the terms of the series is 1 plus half plus 1 by 2 square plus 1 by 2 to the power n minus 1. So you apply the formula for the geometric series with first term 1 and common ratio half, so that the series sum of the series up to n terms is 1 minus 1 by 2 to the power n by 1 minus half. After simplification you will get this. Now you take the limit on both sides, so that limit of the variance of Sn is equal to 2. That means from equation number 1, variance of Sn tends to 2 as n tends to infinity. This means that we do not get variance Sn tends to infinity. Therefore, from corollary 2 of the theorem, Lindberg condition does not hold, and this in turn implies again that Feller condition will not hold. So if Feller condition, both the Lindberg condition and a Feller condition will not hold in this example. However, Sn minus expectation Sn by root over variance Sn is equal to Sn by root over variance Sn, because expectation Sn is 0. So that you take the expectation of this quantity Sn minus expectation Sn by root over variance of Sn. This is equal to 0, and variance is also equal to 1. Why? Because this is the computation 1 by variance Sn into variance Sn. This is 1. If you take root over square root of variance Sn outside this is constant. This will be squared. When this is a square, then the variance 1 by variance Sn will come. So it follows that Sn minus expectation Sn by square root of variance Sn is distributed as standard normal distribution. So this one you can verify by computing the characteristic function Cf of this quantity, which will ultimately ultimately got the Cf of this quantity as e to the power minus half t square. That is the Cf of the standard normal variate. And then applying the continuity theorem, you can conclude this. So this example serves that when Lindberg condition does not hold, then still the central limit law will hold. So when central limit law will hold, but Lindberg condition does not hold. That is why in the statement of discussion of the statement of the theorem, we have said that Lindberg condition is too strong for the central limit law to hold. Why we call it too strong? Because Lindberg condition not only implies the normal convergence, but it also implies the Feller condition. So this is more than requirement. Feller condition is more than what we require. That is why it is too strong for the central limit law to hold. In example 2, we have this probability xn is independent sequence of random variables such that probability xn is equal to 2 to the power n is equal to probability xn is equal to minus 2 to the power n is equal to half, and goes from 1 to 2. So here we compute expectation xn is 0, variance xn is 2 to the power twice n, so that variance of Sn is equal to, here again the same process. You compute, write down the terms of the series up to n terms and apply the formula for the sum of the geometric series, and then you will get the sum as 4 by 3 2 to the power twice n minus 1. So this is the sum. So now take the limit variance of xn by variance of Sn. So variance of xn is 2 to the power twice n in the numerator, and variance of Sn is 4 by 3 to the power twice n minus 1. So you cancel out this, so 1 by 1 minus 2 to the power minus twice n will come, and if you take the limit, then this part will be 0, therefore 4 by 3 will remain. So it follows from equation 1 that limit of the maximum, this is variance of Sn, variance of xk by variance of Sn is not equal to 0. That means Feller condition does not hold, so that Lindberg condition will not hold. Hence we cannot conclude at this moment whether the xn obeys the central limit law or not. We cannot conclude. because both the failure condition, here failure condition does not hold as well as Lindberg condition also does not hold. So hence Lindberg failure theorem fails to say whether the sequence obeys the central limit law. So that is the importance of this example, what the example says. Now I'll give you a homework here. Here xn is a sequence of independent random variables such that probability xn is equal to minus n to the power gamma is equal to probability xn is equal to n to the power gamma is equal to half. Okay, now you have to verify whether this xn obeys the central limit law or not. First you saw that variance of Sn tends to infinity as n tends to infinity. So by computing variance of Sn, by first you compute expectation Sn, after that you compute variance of Sn. So from the expression of the variance of Sn, you will easily verify that variance of Sn tends to infinity as n tends to infinity. After that, you verify whether Lindberg condition holds or not. So while doing that, in condition 3, the integral, there is some integral, here is some x minus mu k greater than epsilon root over variance of Sn. Okay. Now so that you saw here that this set, this integral something is here, this is equal to 0, so that Lindberg condition is satisfied. You have to do this, and by doing that, if the Lindberg condition is satisfied, then surely central limit law will hold for the sequence xn. Okay, this much for today. Have a good day ahead. Stay home, stay safe. So I'll be taking a test next week. The test will comprise of objective type questions, mainly objective type questions, and one or two short answer types. So try to prepare. For objective type questions, you don't need to read the proof of the theorem and others. You have to understand conceptually what the theorem says and what the definition says. After that, I will set objective type questions. At least 15 questions will be asked on objective types. Okay, bye.